Our next causal comparative design is called an ANOVA, which stands for analysis of variance. In this particular case, you're also going to start with a question that says, is there a difference between? But the reason we're going to stay away from t-tests in this case is because we have more than two groups. We have three or more groups. So if I ask a question like, how often do members of 5 particular churches attend services? I might do that with Lutherans, Catholics, Protestants, Baptists, and Jehovah's Witnesses. And I'll get a mean for each of those 5 groups. If I were to run t-test comparing each of those 2 groups, I would have to compare group 1 to 2, 1 to 3, 1 to 4, 1 to 5, 2 to 3, 2 to 4, 2 to 5, 3 to 4, 3 to 5, 4 to 5. So it's roughly 10 different t-tests. Not only do I not want to go through the labor of 10 different t-tests, every time I run one, when I set that alpha at 0.05, I'm saying I'm willing to draw an incorrect conclusion 5% of the time. If I ran 10 tests, I'm going to be wrong on average, half the time roughly, because I ran 10 tests and I'm making an error 5% of the time on each of those tests individually. So what we do about that is we say, when we're comparing the means of more than 2 groups, we want to make sure that our total error over all of our comparisons is only 0.05, and that's what an ANOVA does. So what I'd like you to have open here is back in your folder of graphics of means comparisons, there's a folder of a file called Calculating the F Statistic for an ANOVA, and that's what I want to walk you through here. Consider that we had a test where we had 3 different fertilizers, and we wanted to see how well they make a particular plant grow. So we're going to give these fertilizers to 3 plants, and over time we're going to make observations, 6 specifically, of how much each plant grew in each fertilizer group. So what we're going to do in this particular page, we're going to say fertilizer A1 was observed 6 times, and the plant grew, let's just say, 6 inches, 8 inches, 4 inches, 5 inches, 3 inches, and 4 inches. Then we do the same thing for fertilizer 2, or A2, over the 6 observations. That's how many inches it grew. And for the 3rd observation, that's how many inches it grew. Our null hypothesis is that there's no difference in the plant growth for these 3 fertilizers. The next thing we're going to do is we're going to calculate the mean within each fertilizer group. So fertilizer 1 grew plant 6 inches, 8 inches, 4 inches, 5 inches, 3 inches, and 4 inches. Those were the 6 observations divided by 6. So the average growth within that particular fertilizer was 5 inches. Fertilizer 2 had those 6 observations for an average growth within it of 9. Fertilizer 3, those 6 observations for an average growth of 10 inches. So that's the mean within, keyword, within each fertilizer type. The next thing that we're going to do is we're going to calculate what's called the calculate the overall mean. So what we do is we had a mean within fertilizer 1 of 5, a mean within fertilizer 2 of 9, fertilizer 3 of 10, divided by 3, 24 divided by 3. So the overall mean growth across all 3 fertilizer types was 8 inches. So with that 8 inches, we're going to then calculate what's called the between group sum of squares. And again, the key word here is now we're not thinking about within a particular group of fertilizer. We're looking for differences between the 3 types of fertilizer. So we had 6 observations of fertilizer 1, and its average growth was 5 inches. The overall mean was 8 inches. So we say that N, the number of observations, was 6 times 5 minus 8 squared, between group sum of squared. That's going to get rid of the negative sign. We do the same thing for the 6. The mean within fertilizer 2 was 9. The overall mean is 8. 6 times 9 minus 1 squared. Fertilizer 3, its mean was 10 inches. The overall mean was 8. 6 times 2 squared. We add them up and we get what's called the between group sum of squares of 84. The next statistic that we need to look at is called degrees of freedom. And all the degrees of freedom is the number of groups that you have. In this case, we have 3 different groups, 1 for each fertilizer type. And when you calculate degrees of freedom, what you do is you basically subtract 1 for the calculation that you do. And so it's like having to put a coin in to run a particular test. So our degrees of freedom between group is just simply our 3 types of fertilizers minus 1 to calculate the test for a value of 2. So what we do with that number is we take our mean square between, we divide it by our degrees of freedom of 2, and mean square between divided by 2, and our value comes up to 42 for mean square between. The next thing that we do is basically the sum of squares, but within each group. So what we're going to do is we're going to say for group 1, you had a value of 6 minus its mean of 5 equals 1. Another measurement within group 1 was 8 minus the mean for group 1, fertilizer 1 minus 5 equals 3. We do that for the 6 measurements. Each measurement minus the mean within that group. We do the same thing for fertilizer 2. You can see the mean was 9. So what is each value of each observed mean minus the mean for the entire group? And we do the same for fertilizer 3. That's the first step in calculating the within group sum of square. So we add all of those up, those values, going back to the screen, the previous screen. 6 minus 5 was 1. 8 minus 5 was 3. We squared them because now we're talking about the within group sum of squares. So the difference of 1 squared was 1. The difference of 3 squared is 9. We add them up for all 18 measurements across the 3 different types of fertilizer. To calculate the degrees of freedom, it's a little bit more of a complex formula. Don't worry about it, honestly. But in this particular case, we come up with a value of 15. The degrees of freedom are not really important other than they are related to the actual statistic, the final statistic that you get. The mean square value now is simply the 68 that we got for the sum of squares within, divided by that degrees of freedom, which was 15, gives us a value of about 4.5. So what we have in the numerator are mean square between which was that value of 84 divided by 2, or 42. And in the denominator, we have a mean square within value of 4.5 for an F statistic that equals 9.3.